Thank you, Tavi, for introducing me and for organizing this wonderful seminar series. I know I probably speak for a lot of people when I say that a lot of the seminar series that have sprung up during the pandemic, like this one, have been keeping many of us connected to our international collaborators and our international community. And certainly a lot of the work that I'll be talking about today, really would exist without the wonderful work of many of my collaborators who I'll sort of thank throughout the talk. For those of you who don't know me, my name is Alex Robel. I'm an assistant professor at Georgia Tech in Atlanta, Georgia, here in the US. And today I'm going to be talking, I'm going to be talking about two topics actually. So the first half of my talk will be focused on some of the work that's been done in my group. It'll be kind of an overview of a few different projects that have been done in my group to understand and kind of add nuance to the idea that ice sheets can be either stable or unstable. And so the way that I'm going to organize my thoughts and my slides on that is talk about sort of the ways in which there might be ambiguity about how ice sheets become unstable, so how they go through a sort of destabilization transition, or what might be called a bifurcation, to go from being stable to unstable, and then how, even if they are unstable, there can still be really large differences in what we might project for their behavior. So that'll be the first half of my talk, and then sort of inspired by a lot of the really wonderful and thoughtful talks that I've seen during this seminar series from other glaciologists who have talked a bit about their personal journey and some thoughts about kind of where they think the field is and where it could be going and how we can do better. I'll talk a little bit at the end about some ideas and thoughts that I have for how we can do better to incorporate sort of a wider range of views in glaciology. So with that, I'll start with, my slides will go. I'll start with really something that I think, many of us who, certainly, many people here have been working in glaciology for much longer than I have. But I think something that has been really noticeable, particularly over the last 5 or 10 years, is the real acceleration in public attention on the work that we do. And in particular, a lot of that public attention has been focused on this idea that we are going through some sort of transition, or that ice sheets might be going through some sort of transition from stability to instability. And so here's just a sampling of, literally based on a Google News search of ice sheet stability from the last, 5 years or so, of various articles really looking at different, studies that have come out. But, I think it is worth it to note that we are a small research community, and yet we get a lot of public press attention sort of out of proportion to our size, to the number of people who are doing glaciology. And so I think that that's a really fortunate place for us to be, because if for the most part, I don't ever have to convince, friends and family or, other members of the public who I might meet and talk to about my research. I don't ever have to convince them that this is important, because, the press and, newspapers and are convincing them already that it's important. And so it's really just our job to kind of do science in the most responsible way possible and communicate that information to the public. But this acceleration in interest in ice sheet stability is really part of a longer trend. So here is just a screenshot from Google Ngram, which you can use to sort of search for the appearance of a word or a phrase in the Google Books English corpus. So this is some sort of like representative sampling of books in the English language, and you can graph sort of the appearance of those terms over time. And so I picked a few terms: ice sheet stability, ice sheet instability, and ice sheet collapse, to sort of see how the usage of those terms has increased in time. And what we see is we are kind of at a high point, at least summed over these 3 different terms, although for whatever reason, maybe someone else who's been in the field longer can tell me why ice sheet collapse really had a boom in popularity in the 90s and then collapsed, as it were, in popularity in the early 2000s. But really, there's been a steady increase in sort of focus and attention on the notion of ice sheet stability. But of course, this isn't really new. We can go back hundreds of years to a lot of indigenous oral traditions, which tell us a lot. So in particular, there's been some really excellent work done, and so I'm just sort of showing one example here, looking at indigenous traditions from the Tlingit people in Southeast Alaska, who have a really extensive sort of oral narrative and sort of oral record of glacier surging and collapse sort of over timescales of like hundreds to even thousands of years. And this really predates by a long time the arrival and the beginning of records from settler scientists who sort of started coming in the 19th century and sort of talking about sort of the glacier stability or the relative glacier stability at that time. And so this rich oral tradition gives us a much longer time series, and sort of analogous to the idea that a lot of historical records of glacier change that we have from aircraft span a much longer time scale than the short satellite record. This indigenous tradition gives us a much longer history for thinking about ice sheet stability and gives us a sort of a much broader perspective about what ice sheet stability might look like. And that, of course, extends to actually indigenous oral traditions throughout North America. So, for example, here in Georgia, which is originally the land of the Muskogee people, where I do my work, there is also a long oral tradition of sort of the movement of people in response to climate change in this part of the world that was largely affected by large changes in the North American ice sheet complex at the end of the last glacial period. So there's really a lot that we can learn, even going back, prior to this very, very recent period of interest in ice sheet stability. But sort of getting back to this modern focus on ice sheet stability, this recent acceleration in public concern over ice sheet stability has also been paralleled by a push within our community and at funding agencies, both in North America and in Europe, and really just all over the world, a push in our community to translate this fundamental science on ice sheet stability, which goes back 50 years, into more reliable projections of sea level rise. So examples of this sort of new push to really focus on translational science is included in these reports, like the How Much, How Fast report from a few years ago, the Tipping Points project from the EU, and of course the ITGC project, which many of you are involved in across the US and UK glaciology communities. So even with this real increase in focus on ice sheet stability, what we see is that, I think something that many of us know and sort of grapple with on a daily basis in our research is that there's still a massive amount of uncertainty in our projections of sea level rise, despite all of this renewed interest and sort of acceleration in the science that is being done on ice sheet stability. And the interesting thing about this uncertainty in sea level projections is that, so I've taken a few sort of three prominent examples of this. The top left corner is from the new ISMIP-6 compilation or intercomparison project for Antarctica, led by Helen Sorosi. So here's one figure showing many different ice sheet models forced by the same climate model, how they would project Antarctica contributes to sea level over the last or over the next century or so. And then two kind of prominent studies that have received a lot of attention in our community by DeConto and Pollard in 2016 and Nick Gollage and colleagues in 2015. And a commonality between these projections is that there are larger differences in projections between models or model versions, which are all undergoing instability, than there are between models that are models which are staying stable and those which are becoming unstable. So to put that another way, that was a complicated statement. The question of uncertainty is largely dominated by not whether the Antarctic ice sheet will become unstable, but rather what will happen to it once it becomes unstable. And so, just looking at, for example, the ISMIP-6, these top 3 or 4 models, which you can see at the upper end of the range here, which provide the largest contributions to sea level rise. These are all models in which West Antarctica has started to become unstable before 2100, right? So this is the beginning of sort of the canonical marine ice sheet instability that is being simulated in these models. And then the models down here sort of hovering around 0 are those in which West Antarctica has not yet started to undergo a sort of runaway instability in the way that we might traditionally think of it. So the point here is that, many of our questions of uncertainty can't be answered by simply deciding, is the ice sheet stable or unstable, or will it become stable or unstable? But really the largest questions of uncertainty are, when will the ice sheet become unstable, and what will happen to it once it becomes unstable? What other processes will start to play a role that will modulate the rate at which the ice sheet contributes to sea level rise once it becomes unstable? So that's really what I want to talk about today, is sort of some of the work that we've been doing in my group to interrogate these questions. And I also don't in any way want to give off the impression that we are the only people or the first people who are doing this. There has been a lot of excellent work being done within our community, particularly in the theory and modeling parts of the community, but really, throughout the glaciology community, to really push beyond this stability instability binary and start to answer more nuanced questions about the threshold for instability. So looking at differences in the timing and likelihood that ice sheets will become unstable, and then also looking at differences in the rate of retreat once an ice sheet becomes unstable. So I really want to give, there are too many people doing too much excellent work, to name all of them here, but there are a lot of excellent people working on this problem. And so I'm just really going to touch on a few problems that we have been working on in my group. Okay. So the first set of ideas I want to talk about is sort of, how do ice sheets lose stability? And so the first one is a question about ice shelves. These are the floating parts of ice sheets, which buttress the flow of ice coming from grounded on land. And a question that we wanted to answer, and that many people have wanted to answer in the past, is what controls the speed at which an ice shelf goes from this example on the left-hand side. So this is sort of the famous pair of images from Larsen B ice shelf in 2002. So this is January 31st, and then on the right, you have an image from Larsen B about 5 weeks later, when it had completely collapsed. So that was a 5-week time scale of collapse, yet there are examples of other ice shelves from throughout the Antarctic Peninsula, which has also undergone sort of collapse or disintegration, or whatever you want to call it, over time scales that are longer, right? So over time scales of seasons, or over time scales of years or decades. And so what controls that speed, whether an ice shelf disintegrates over weeks or over decades? So we wanted to get at this question, and so this is work that I did with Alison Banwell, which was published in a paper in GRL back in 2019. And the way that we wanted to approach this problem was specifically to look at the case that is relevant to Larsen B, which is the filling of melt ponds on the surface of the ice shelf, and then the draining of these melt ponds and how melt ponds interact with each other. So what we did was we built a cellular automaton model in which ponds randomly fill up over a 2D lattice or sort of 2D network lattice of ponds on an ice shelf, and you can randomly place these, or you can place them in a grid. It doesn't really affect the results too much of what I'm about to talk about. But the idea is that these ponds randomly fill up, and then they reach when they reach a certain threshold, the ponds drain. So this is sort of akin to what might be predicted in a Nye-Zero stress criterion for fracture, or a linear elastic fracture mechanics framework for fracture. The melt pond reaches a threshold, at which point it drains, and it stresses the melt ponds within a certain radius around it, right? And so we can control that radius at which melt ponds affect the ponds around it. So when it stresses those ponds, it lowers the threshold for those melt ponds to reach hydrofracture. And so what I'm going to show here, or what I'm showing here, is an animation of those melt ponds randomly filling up. The blue colors are sort of the depth of water in those melt ponds. All of these numbers are non-dimensional in this model. And then what you can see are the areas that are black are areas in which the melt ponds have hydrofractured. So what happens is, when a single melt pond hydrofractures, it can trigger other melt ponds around it to hydrofracture in sort of what we call a hydrofracture cascade that eventually sort of causes the entire ice shelf to be damaged and to sort of reach a state of collapse. And what we found from here is that ice shelves cannot collapse arbitrarily fast. And that's because melt ponds have a limited area over which, or a hydrofracture event has a limited area over which it can affect the melt ponds around it. And that is fundamentally set by the flexural properties of ice, right? Flexure is localized on a 2D surface. And for sort of a really broadly realistic range of parameters, what we find is that the collapse speed is never going to span the entire ice shelf on a time scale of, sort of a few melt pond iterations. Now, of course, if we add a lot of meltwater to the ice shelf all at once, you can cause it to hydrofracture arbitrarily fast. But then, of course, you need a way to explain, why that melt pond, or why that melt appeared from 0 to, a large volume in a really short period of time. And this might actually be a good way to potentially explain why Larsen B collapsed so quickly, because the 2001-2002 melt season was a very anomalous melt season for Larsen B, in which the increase in melting over the course of the melt season, as melt ramped up over the season, was 3 times faster than sort of the typical seasonal average before that. So Larsen B really might have been sort of a special case in which sort of a very extreme year caused the sudden appearance of a lot of water and this very fast ice shelf collapse. And so the importance of this, of there being sort of this speed limit to ice shelf collapse, at least for this hydrofracture mechanism, is that the speed of ice shelf collapse heavily influences the speed of subsequent retreat through either viscous or fracturing properties. So there's been 2 really great studies in the last few years by Fiona Clerk and colleagues at MIT, and Sun and colleagues through the ABU-MIP intercomparison project, basically looking at how quickly calving would occur if you removed an ice shelf over various timescales. And also that's for the Clerk study. And then for the Sun study, or for that the ABU-MIP intercomparison project, that's just looking at sort of more typical, viscous responses to the rapid removal of an ice shelf. And basically what both studies find, sort of broadly speaking, is that the response of, how quickly ice is lost after you remove an ice shelf really strongly depends on how quickly you remove that ice shelf. And that is down to the time scale of sort of days. Like the difference between 1 day and 10 days and 100 days leads to a very, and 10 years leads to a very large difference in the rate of ice sheet mass loss subsequent to that ice shelf collapse. So this sort of question about how rapidly you can remove ice shelves is quite important. And of course, so we've done all this in a very simplified model. We kind of wanted to just prove a point about sort of the dynamics of melt pond networks. But in reality, melt ponds have complex hydrology, and so really excellent work is now being done on this problem by now, unfortunately, former postdoc of mine, Sammy Buzzard, who now just started her new job as a lecturer at Cardiff. But so Sammy is the lead on the Monarchs project, and the idea here is to build a new three-dimensional model for the coupled hydrology and glaciology of ice shelf surfaces. So you can see here on the right is an animation showing an example from Roy-Baudouin ice shelf in East Antarctica. And so what Sammy is showing here is by randomly placing water on the surface of the ice shelf and then allowing sort of hydrological processes to drive the water to low elevations, you can sort of see the appearance of these melt streams and also isolated melt ponds that can also be seen in satellite images of the surface of this ice shelf. Okay, so moving away from ice shelves, the next question that I want to tackle here is what happens, so after you've had you know, an environmental change, what determines the likelihood that a grounding line will become unstable, right? So this is actually a very classic problem that has been worked on by a lot of people, and so I'm just going to break off one small piece of that and talk about that today. And in particular, what we're looking at here on this first page or on this first slide is the magnitudes of the value of a particular parameter, we call it gamma, that we have derived, that this parameter gamma basically measures in sort of a perturbative fashion. So like, you know, the point here isn't to take the magnitudes of this so seriously so much as large changes in this parameter are places where the bed slope changes very quickly over space. And these are places also where the bed slope can potentially play a large role in setting the grounding line stability. So in the classical idea of grounding, or the sort of classical theory of grounding line flux, the only thing that comes into determining the grounding line flux is the bed depth, right? And what that leads to is sort of this theory for the marine ice sheet instability, that where the bed depth gets deeper towards the interior of the ice sheet, right? We call these retrograde slopes. You can potentially have a positive feedback and an instability that leads to retreat without forcing. The assumption in that original theory is basically that the bed topography is negligible compared to the surface topography of the ice sheet. And so what we do here is we basically extend this theory and we use this parameter, which is plotted here for Antarctica based on bed machine data, to show places where the theory might break down, the original theory might break down. So places where this value is large, so pink or green on this map, are places where we expect that a grounding line moving over that area is going to be significantly different from what would be predicted by the theory. And in particular, I'm just going to show sort of two zoom-ins of the Amundsen Sea sector and the Cyprus coast, which is basically to show that even though our traditional idea of West Antarctica is that you know, the bed is, you know, relatively subdued compared to, let's say, Greenland, and relatively flat, the bed is actually quite bumpy from the perspective of grounding line flux and stability. That is to say, bumps on the bed will potentially have, you know, relatively small bumps on the bed will potentially have a significant influence on the bed topography. And so I'll show why that's the case here in some simple simulations. So what I'm doing here, sorry, I should also say all of this work that I'm talking about here is a collaboration with Sam Pegler, Jenny Catania, Dennis Felix, and Lauren Simpkins. And there's also a lot of observations that go along with it that I'm not going to talk about today, but I'm happy to talk offline with anyone who wants to talk about sort of the larger context of this work. But so what we did here is we did a series of very simple simulations using a 1D flowline SSA model. And so we assume these four simple topographies where you have a sharp bed peak. Although the sharpness of it can be like less sharp than what I'm showing here, the results are all qualitatively the same. So you don't need to focus on that sort of aspect of it. But the point here is that the bed is certainly sharper than what is typically assumed for a grounding line stability problem. And the sharpness of this bed is really trying to mimic the fact that in reality, subglacial topography is jagged compared to what we typically assume in sort of a, what we might call like a mismip type bed setup. And so the prediction from the conventional theory is that you will have a stable grounding line on the prograde slope here on sort of the far side of this bump. And as you lower surface mass balance, for example, your steady state of your grounding line will approach the bed peak, and then it'll disappear when you get to the bed peak and you go through the marine ice sheet instability. But when we actually calculate the steady states in a 1D SSA flowline model, so all of the sort of basic assumptions are the same, except we're not are the same as what goes into the canonical theory, except we're solving the numerical problem. What we find is these four lines, these four colored lines, show the various steady states of this system. And so what you can see here is that in reality, the steady states continue further down to much lower SMBs than what would be predicted by the traditional theory. And this is because, well, I'll talk about in a second why this is because, but so, one lesson that, the first lesson that we gather from this sort of simple example is that grounding lines at sharp peaks are actually regions of enhanced stability. The grounding line is going to want to stay at or near a bed peak for a much larger range of climate forcing than would be predicted by sort of our old theory. The second point to make here is what we've done here is transient simulations where we look at the response to a step reduction in surface mass balance. And what you see is this behavior where the grounding line will transiently retreat to the bed peak, persist, and then spontaneously retreat. The climate doesn't change after year 0 in this simulation. But the transient behavior is such that it produces sort of this illusory stability or this kind of like false stability where the grounding line just hangs out at the bed peak for a long time while the interior of the ice sheet adjusts to the change in surface mass balance before finally spontaneously retreating. And so the reason why this happens can be illustrated here in a really nice graphic that Kaya Riverman made and posted on Twitter. So thanks, Kaya. And the basic idea is this: is that when you have a bed peak, right, a sill or a peak in front of an over deepening that an ice sheet has a grounding line in front of, the ice, in order to reach the grounding line, ice has to go up the sill, right? By definition, if you have a retrograde slope, ice has to traverse the retrograde slope in order to get over to the peak where you might have a stable grounding line position. But the point is that in going up that retrograde slope, the ice is going to slow down, and that reduced driving stress is going to be transmitted to the grounding line through longitudinal stresses. And we can sort of show all this nicely in the model. And so the point is that when a grounding line starts to reach a bed peak, or when it gets close and closer to a bed peak, the influence of the retrograde slope from upstream is going to start to become very important for the grounding line flux at the grounding line itself, that is at the bed peak. So we're no longer in a world in which the grounding line flux doesn't see or doesn't care about the bed slope or the changes in bed slope that occur upstream. Those changes in bed slope are very, very important for determining the stability of the grounding line. And so you can look sort of in a number, once you kind of know what to look for, you can look in a number of different complex ice sheet models. Everything I've shown so far is in a very simple idealized 1D SSA setup. Really just in order to prove a point, we're sort of redoing these experiments now in a full Stokes model. But you can look in other complex models for real glacier geometry. So these are 3D, higher order models. Or some of them are higher order models, some of them are hybrid, and basically you see these pauses on bed peaks all over the place in these model results. So, this sort of behavior of one, enhanced stability at bed peaks, but also potentially, false stability at bed peaks, which I know are sort of two contradictory things. Both are possible, and we sort of need to figure out, you know, for any given bed peak, which is occurring, whether a grounding line is actually stable at the bed peak or whether it's sort of a false stability that will eventually lead to instability. This sort of thing is happening all over the place in models, and I think, as I made the argument before, it's something that we should expect will happen quite a lot in reality, and that's just because subglacial topography is way bumpier than we give it credit for. Okay. Oh, and so finally, on this sort of this last slide of this first part, I just want to preview some really interesting work that's being done by John Christian, who just started a postdoc this last year with myself and Ginny Catania. What John is showing here is that the likelihood that the marine ice sheet instability will start is sensitively dependent on the geometry of the bed peak, but also the characteristics of internal climate variability. And so I'll talk a little bit more about climate variability in a few slides. But the idea here is that John is really trying to understand when we observe a rapid retreat of a glacier over a retrograde slope, whether we can attribute that rapid retreat to a trend in climate, you know, due to, for example, anthropogenic climate change, or whether, you know, it might be caused by internal variability of the climate, right? And so parsing these two possibilities out is actually quite tricky and really requires us to adopt a sort of probabilistic or statistical way of looking at the probability of retreat given the background variability of climate. And so what he's showing here in these this sort of postage stamp plot here is that the probability of retreat over a bed peak onto a retrograde slope is really sensitively dependent on small changes in the height of that sill. So this is changing the height of the sill over 10 meters, which is well within the uncertainty of most of our bed topography products, and also small uncertainties in the amplitude of climate variability, which is forcing this glacier. And so this has important implications for sort of how we attribute observations to climate change. And you know, John is starting to write up a paper now, which, you know, hopefully you'll all get to see in the near future. Okay, so we talked a bit about so far about how glaciers lose stability, and now I'm just going to give a sort of a quick overview of some work that we've done to think about how rapidly glaciers retreat once they have become unstable. So for rapidly sliding glaciers, which is sort of many of the glaciers that we're the most concerned with becoming unstable, we have found in a sort of sequence of studies, one led by John Christian at the end of his PhD, and then another by myself, Gerard Rowe, and Marianne Hasselhoff in JGR in 2018, that the two slowest modes or, you know, you can think of them often, they're called eigenmodes, but basically they're the two slowest modes in which a glacier that a glacier uses to respond to a potential forcing, right? So you can decompose the response into sort of an infinite number of modes, but the response is dominated by the two slowest modes of marine terminating glacier sort of dynamics. And these two slow modes, which we call the slow mode and the fast mode, or really it should be the slow mode and the slightly less slow mode, they actually become unstable at different thresholds of retrograde slope, right? So the slowest mode is actually the mode that we traditionally associate with marine ice sheet instability. And that mode sort of kicks in basically when the bed becomes very weakly prograde, or basically at a flat bed, right? So this is our traditional way about thinking about marine ice sheet instability happens on retrograde slopes, and that's when this slow mode, that's when it becomes unstable. But that slow mode actually evolves on timescales of millennia. And many of the observations that we are having now and the modeling that we are doing now of glaciers becoming unstable due to the marine ice sheet instability and then sort of rapidly evolving you know, over timescales of like decades is actually a destabilization of this faster mode of the marine ice sheet instability. And so, but the bed has to be steeper in order for this sort of fast mode to be engaged. So the idea is that basically, like, there is actually no one marine ice sheet instability. There are many marine ice sheet instabilities, and they occur at sort of different thresholds of bed slope. And when we think about sort of these retreat rates that we talk about sort of in West Antarctica or in Greenland, of like order hundreds of meters a year to kilometers a year of retreat, this is really a fast mode response of glacier instability, but that will only occur if the bed slope is sort of the order of sort of degrees, sort of, 10 to the -2 rather than 10 to the -3, which is what we might typically associate with the marine ice sheet instability. Okay. So the last point that I want to talk about is another study that we had. So this is with Helen Sarosi and Gerard Rowe in PNAS 2 years ago. And I'm really just going to highlight kind of the main result from this, which is that the other upshot of this idea that like you can have different speeds of the marine ice sheet instability is that when a marine ice sheet becomes unstable, its response to climate variability starts to become very important, right? So traditionally, we would think that glaciers are integrators of climate noise, and that a stable glacier will basically damp out all of the sort of year-to-year noise or decade-to-decade noise in climate to produce sort of a statistical steady state. But when you have an ice sheet that's become unstable, the instability amplifies the glacier's response to climate variability rather than damping it. And this is actually quite important for projections of future ice sheet change. So here's an example from this paper where what we do is we run an ensemble of simulations for Thwaites Glacier under decadal variability in ocean melt. So everything is the same, all the parameters are the same. The mean ocean melt is the same between all of these simulations, but all we've done is we have stochastically generated decadal variability in ocean melt, approximately of the magnitude that we would expect is actually occurring at Thwaites, based on some observations and modeling that's been done there. And then we run a 500-member ensemble of simulations of Thwaites evolution over the next 1,000 or so years. And basically what we see is that in the middle of Thwaites Glacier unstable retreat, sort of through its retrograde slope, which has been simulated in now many studies, the width of the possible Thwaites contributions to sea level rise, sort of the probability distribution, the width of it is at its maximum, and it increases the fastest when the glacier is the most unstable, right? So there's a difference between the glacier just having become unstable. We still have a pretty good projection, a sort of constraints on the projections of it, from when it's in the middle of its instability and it's retreating the fastest through its sort of retrograde basin. And you have from one glacier, just due to internal climate variability, order 10 centimeters worth of uncertainty on sea level rise. So, you add this up over many glaciers, and then of course you add in all the contributions of other kinds of uncertainty, which people have done some really excellent work in the last few years looking at sort of parametric uncertainty in ice sheet models, and you really start to add up a lot of uncertainty, right? And so adding in this irreducible uncertainty that comes from climate variability that we're never going to be able to, predict 500 years in the future if we're looking at these long simulations, this starts to become really important to the overall picture of, how uncertain are our future projections of sea level rise. And so we're trying to tackle this problem in sort of two new projects that are funded by NSF and the Heising-Simons Foundation. And basically the idea behind the two projects is that we're trying to find a middle ground between very, very simple models, mostly statistical models, or what might often be called semi-empirical models, projecting future sea level, sort of usually trained on modern observations or trained on paleo observations, which fundamentally have an issue of sort of what kind of range of sea level change are they sampling, and then very complicated, but very process rich and accurate ice sheet models, which are sort of the state of the art now, which excel in their job of including as many processes as possible, but of course they're computationally expensive and it's hard to run large ensembles of them. Although there's some really excellent work being done now with emulation using machine learning of these kinds of models. So the idea is we want to sort of have a middle ground where we take an ice sheet model. We're using ISSM in the one of these projects, stripping out sort of everything except for what we would call like the dynamical core of the ice sheet model, basically mass conservation plus velocity, and then replacing the process parameterizations and the climate forcing with stochastic parameterization. So we're calling this the stochastic ice sheet model. And basically we're trying to just think of sort of a parallel way to move forward with developing ice sheet models in order to sort of make some progress on quantifying uncertainty and attributing past ice sheet change. Okay, great. Okay, so this is going to conclude sort of the more science-focused part of my talk. And I'm happy to take questions on that at the end, but I just want to spend a few minutes here giving a little bit of perspective on, some thoughts I have about sort of where we are as a field and sort of, who we are as a field. And particularly these are from my perspective of, someone who, one, grew up in a place that almost no other glaciologist did and kind of had an unlikely journey to become a glaciologist. And also I'm at Georgia Tech. I'm here sort of in the heart of the southeast of the United States, which is a place that is not at all known for glaciology, but is at the center of vulnerability to future sea level rise. So I just want to talk about these themes here for a few minutes. So I've been talking a lot about these like centimeters or meters of uncertainty in sea level rise, and it's often in these discussions, I think it's easy to lose sight of the fact that like, what is a few centimeters of sea level uncertainty mean? So I have this plot, which I love to show in public talks, which shows the distribution of the world's population relative by elevation. Right, so the pink line here is basically the percentage of the world's population and where they are with respect to sea level. And the thing that I want to point out here is that when you get really close to sea level, people really love to live near sea level. Usually coastal areas are nice places to live. I certainly should know, I grew up in one. At really close to sea level, for every additional centimeter of global mean sea level you add, you expose an additional about 1 million people to flooding, just from high tides, normal sort of day-to-day or week-to-week flooding. So when we talk about sort of centimeters of sea level uncertainty or 10 centimeters of sea level uncertainty, we're talking about millions of people who can possibly be affected by these issues. And so here in the Southeastern United States, this is like a very real and present issue. This is not, Thwaites Glacier instability in 500 years. This is stuff that is like happening now here. So here is an example from coastal Georgia. This is Highway 80, which goes from Savannah, Georgia, which is a beautiful city sort of on the mainland, but just near the coast of Georgia, and it goes to Tybee Island. So Tybee Island is a small coastal barrier island community of about 3,000 permanent residents. It's also a popular vacation destination. And this is a picture from 2015 during a spring tide. There was no hurricane, there was no storm. This is like a pretty normal, approximately monthly occurrence, this tide. And the highway flooded. This highway is the only way for residents on Tybee Island to access Savannah, and all medical and emergency services in this area are all located on the mainland. So basically this like fully cut off the residents for a period of about half a day. And when this is a thing that is regularly occurring, this is just one example of this sort of flooding that occurs. And of course, to anyone who works in this field, like this is unsurprising, right? So the bottom right histogram here, the blue line shows the high tide probability distribution in the 1930s when this highway was originally extended out to Tybee Island, and the red line shows over about the last 5 years the high tide distribution. And the gray dashed line is the elevation of Tybee Island. So basically, when they built this highway, it was, well below high tide mark. And so that was a smart decision for them to make. And of course, that's no longer the case. And they've already spent a few $1 million to raise the most vulnerable portions of this island. But the point here is that, this is a thing that is already occurring and that is costing a lot of money to residents here in coastal Georgia. So before I talk about my next example, I just want to, actually, let me just show the next example and then I'll come back to this other slide. So in my hometown of Miami, Florida, this is an even more present problem. So here's just one, picture. You can go find 1,000 like it on the internet of basically a normal week, a normal month in Miami Beach, which is also a barrier island off the coast of sort of the main city of Miami, where lots of people live, hundreds of thousands of people live on the beaches in Miami. And just in the last 5 years, the city of Miami Beach has spent $400 million to raise a few key roads and to upgrade their stormwater infrastructure, just to deal with existing sea level rise. And that'll probably last them about another 20 or 30 years at sort of current rates of sea level rise. On the right is a potential plan from the US Army Corps of Engineers to build a seawall pretty much across, or a flood barrier, they call it a flood barrier, over a good portion of Miami. It actually doesn't extend through all neighborhoods in Miami, and you can ask the question of how they decide which communities are worthy of building flood barriers and which aren't. This sort of a topic for a fully different talk. But I want to give you this context because this is something that I think about a lot every day, and it's something that when I go home, when there isn't a pandemic, to visit my family and see my friends, that is something that we of course end up talking about a lot, particularly with respect to my work. And so this is something, here we go, that I bring with me a lot when I do my work. So just to give you that context, so I was born and raised in Miami, Florida. I grew up, my mother is a immigrant from Bolivia. She lived in Argentina for a while when she was in school, before she was jailed by the military regime there in the 1970s, and then moved to the United States to pursue a life here, and then I came a little bit later. And my childhood, was filled with the outdoors, and I was highly encouraged in science, which I know cannot be said for many people, and so those are privileges that I really had. But I lived very far from snow, ice, and mountains. The first time I ever saw snow falling from the sky, I was at college. I probably lived about a 10-hour drive growing up from like the nearest respectable mountain. The reason why I got on this path that I did was because I was lucky enough to attend a public science-oriented high school where I was interested in earth science and physics, and one of my teachers got me a job, an after-school job at a federal lab, which we were actually half a mile from. So that was, obviously, immensely, sort of lucky and sort of privileged of me to have that opportunity. And many of my early experiences, particularly with coastal hazards, I lived through, two of the most active hurricane seasons on record when I was about to graduate high school in Miami, and lived through a lot of devastating storms. And so I went to university and I pursued physics and earth sciences, and I thought that I was going to study hurricanes, right? That was a very logical thing for me to do because of where I grew up. But I had some very influential early mentors, particularly among them Susan Lozier, who's actually now my dean at Georgia Tech. As an undergrad, she was my research advisor, and then in grad school, Elliot Superman and Christian Schuf were my PhD advisors. And really through these interactions with them, and others in the glaciology community, I think two things really drew me to glaciology and really ended up modifying my path from sort of where it had been going, which is that one, there is so much fundamental science that is yet to be done. And that's actually not the case for, a lot of other areas of science, or at least, to me, it didn't seem that way. And two is that I was able to see how this science would directly impact the community that I came from. And, so that's sort of, what I've been speaking to with these, with these issues. And in particular, this is important, or thinking about sort of, how we get into glaciology and then who we let into glaciology is important, because the coastal communities with the highest what's called social vulnerability, or just generally vulnerability to sea level rise, are overrepresented, particularly here in the Southeastern US. So sometimes I think we can get this picture that like people who live on the beach, or people who live in coastal areas, are like privileged homeowners who can just like choose to pick up and move elsewhere, or to bear the cost of rising flood insurance or these things. But in particular here in the US, in the Southeastern US, these Southeastern or these coastal tracts that have really high vulnerability are also much more likely to be sort of targets for what are called managed retreat strategies, right? Which is sort of a euphemism for saying, telling people that it is not tenable for them to live there anymore and to move somewhere else. But of course, there's no historical context for that. Why are these places more vulnerable? Why are they more socially vulnerable to sea level rise? It's because those areas, which are, largely filled with Black and brown people, have been historically underinvested in, and in sort of in terms of their property and their flood management infrastructure. So there's no, even though we're telling people that, maybe they need to leave now, there's sort of no accounting for, kind of what led to that point. And this is, getting to this point, when we talk about co-producing knowledge, or when we talk about sort of making sea level projections that coastal communities can use, we need to think about how we are deciding, what is useful information, and how we are producing this information, and who is producing this information. So something that is often talked about, there's this great paper by Liz Ulte and colleagues, which I would highly recommend folks to read. We talk often about co-producing knowledge, which is the idea that stakeholders who will use the information and scientists work together in order to sort of set a research path and to sort of decide on the most useful way to produce scientific knowledge. And this is often done through intermediate organizations, which can be really valuable to doing sort of effective knowledge production in science. But part of the reason why co-production is necessary in the first place is because we see ourselves as a scientific community as being distinct from the communities that we hope to serve with this knowledge. And of course, to me, that's always seemed ridiculous, because of course, I'm talking to friends and family who are very, very concerned about sea level rise, are concerned about will their children be able to live in the same place that they grew up, and these sorts of existential questions. And the reason why this is particularly a problem is because we know, or we have pretty good rough estimates, which indicate that glaciology and polar science in general are really profoundly unrepresentative of, one, the larger scientific research community, the broader communities that we're in, but in particular, those communities that are most vulnerable to ice sheet change. So I went on the internet and I looked for the best statistics that exist. And so there's a great paper that I'm sure many of you know, by Christina Hulba, from looking at the percentage of female, well, this figure in particular looks at the percentage of female authors in IGS journals over the last 70 years or so. And basically what it finds is that there's been an increase, but female authors still make up a kind of vast minority of authors, both first authors and just generally authors on IGS papers. This bottom plot is from the British Antarctic Survey, and this is actually pretty much the only data that I've been able to find anywhere looking at the racial and ethnic demographics of the glaciology community. And this is actually even just a subset of that. So what they look at here is sort of the broader UK society demographics, the UK higher education system, and then what they call UK polar science, but really this is demographic information taken from passe, you know, which I guess you could say might be in some ways representative of the whole polar science in the UK. And what you can see here is that across gender, across ethnic and racial lines, across disability and LGBTQ plus representation, our field is doing really, really poorly. But we don't even sort of know, I mean, we know that this is a problem, but we don't have detailed information about, you know, why this is a problem. So, you know, the first thing that I would recommend is, one, we could be doing a lot more to gather more detailed demographic information from IGS members. You know, we hold symposiums, we, you know, have journals, you know, we have email lists that we can use to sort of solicit voluntary and anonymized information to get a sense for who we are. So that's point one. Two is to recognize that when we recruit students, and actually we're in grad student recruitment season now, so this is sort of, you know, an important point, I think, is that diverse students have diverse motivations. Not everyone gets into glaciology or gets interested in glaciology for the same reasons that we or our advisors did. And when we read an application and, you know, which has a personal statement on it, and we try to see ourselves or our advisors or other successful people in the people we're recruiting, you know, we often really cut off the possibility that new people with new perspectives who maybe have different reasons for wanting to study this want to be in our field. So this is just a few examples here. I'm going to go a little bit quickly here because we're running out of time, but here's a few examples from folks in my group who sort of contributed what their motivations for getting into glaciology were. And it sort of spans the gamut of sort of, you know, hard science using math to, you know, solving societal problems, helping coastal communities, you know, this sort of range of motivations. Three is sort of an idea that I've been trying to work on for the last few years, but the idea comes from this really great paper on building an anti-racist lab by Cheruri and Beta in 2020. And this, one of the points made by this paper is that if we want to attract sort of a more diverse range of scientists, we need to provide a wider range of on-ramps for students. And what does that mean? That means that even though we're sort of stuck in our ways of like, these are the methods that we use, and this is the way that we do science, or this is the kind of science that I do, allowing for a wider range of possibilities for doing different kinds of science that people with different backgrounds or, you know, different levels of preparation can get involved in the science. For me, like, I come from obviously a very sort of theoretical glaciology background, but if that was the only science that I did, or that was the only science I had undergrads doing, I can imagine that I would have a very poorly representative group of people doing glaciology in my group, and that's really not what I'm trying to do. So I've tried to go outside my comfort zone by getting involved in experiments, by doing more paleoclimate, paleoglaciology, and working a lot more with remote sensing data in order to allow for the possibility that, you know, people who might want to work with me might not necessarily want to only use the tools that I am the most comfortable using. Okay, and so the last point is that we need to create and support vertical and horizontal mentoring spaces. And so what do I mean by vertical? I mean, like, traditionally we think of sort of vertical mentoring structures within academia as ways to like transmit knowledge and you know, to support students who are trying to enter into sort of glaciological research. But it's equally important to set up and support these horizontal spaces. So what I mean by horizontal is that people of similar career level can work together to learn something new, or can just work together to support each other in you know, advancing in their careers, in networking, in, you know, developing new skills. And so we have a lot of really great organizations within glaciology and polar science. Just a few examples here are the EGG group in IGS, Pride in Polar Science, Polar Impact. We also have other really great programming. So a lot of the hack weeks that have sprung up in the last few years, JERP, the Cart House, and Fairbanks Summer Schools, the Girls on Ice expeditions. These are just really great ways to bring new and different people into our field and to support them while they are here or when they get here. And we really need to think about sort of institutionalized ways for providing support to these groups, because in many ways, these are doing a better job of retaining new and different people in our field than sort of a lot of our traditional mentoring methods. So I just wanted to put a plug for those. Okay, so I'm gonna wrap up here, and I just wanna say thank you to you all for listening to me for an hour. And if you have any questions beyond what I can answer now, you can feel free to email me. And I also want to say a big thank you to all the folks in my group and folks who've been in my group in the last few years who are pictured here, and all of my collaborators on the projects that I've talked about today, and of course, my funders down on the bottom right. So thank you all.
Thank you very much indeed, Alex. Some really powerful statements there. Are there questions for Alex? I'd like to say that one of the things that makes me enthusiastic about these IGS seminars is the ability for us to make our science accessible to a broader range of people who can't be here when we are at AGU or a conference. You know, this can be much more broad and allow a much wider range of people to come along. Any questions for Alex?
I have a question.
Go ahead.
Yeah, I was just going back to what you said about the kind of stable, unstable binary at the beginning. I wondered if there's like a criteria that is used to kind of define when a grounding line migration is in a period of like stability or instability. Like, I mean, and like over which timescales that can be defined as.
Yeah, so I think that's a great question. I think when I was talking about sort of like slow versus fast marine ice sheet instability, this is sort of an example of the fact that while I think the criteria that we traditionally think of for the marine ice sheet instability at least is sort of prograde versus retrograde, right? When you're on a retrograde slope, you're unstable. When you're on a prograde slope, you're stable. And the point that I'm trying to get across is that it's not as simple as all that, because ice sheets evolve on many timescales, right? So that prograde versus retrograde distinction or dichotomy only applies to the slowest mode of ice sheet retreat. And that's actually not the one that we're typically talking about when we're talking about like unstable retreat in terms of observations or, you know, sort of modeling studies. So like, yes, there are criteria that can be defined, but I don't know if it is useful to like focus on one or, you know, even a few, because basically it depends on the question you're asking, and it depends on the retreat rate that you're interested in, you know, sort of the criteria that you would derive. So this was sort of the point of, you know, we need to sort of go beyond this idea of thinking like, well, it needs to be one or the other. You know, there's sort of a whole spectrum of things that can happen in between those two. And so we need to explore the spectrum rather than just trying to classify things into these two bins of stable or unstable.
Okay, great, thanks.
Any further questions? Just pop an indication into the chat, or just switch on your microphone and give a shout out. Roger, go ahead.
Yes, thanks very much, Alex. Tremendous presentation, really enjoyed it. In your modelling of the retreat rates, were you able to take into account surface elevation and you know, the rise in surface elevation? And I ask it just, I was reminded of what we heard in Regine's presentation last week about how some glaciers can retreat into higher altitudes where it's colder and then end up more stable.
Yeah, I think so. I guess some of the simulations that I show, I mean, all the simulations that I showed sort of include that possibility. I think mostly what I've talked about today is a marine ice sheet instability, which is sort of one topic of focus. I think the idea that you're talking about is the other main instability that people talk about in glaciology, which actually goes by many different names, but it basically has to do with the height mass balance feedback in mountain glaciers and in land-based ice sheets. And I actually have an undergraduate student, Hannah Verbancourt, who is currently applying to grad school right now, who is actually looking at how these two kinds of instabilities, or these two feedbacks, the sort of marine ice sheet instability and also the height mass balance feedback, how they interact with each other to potentially change the speed of glacier retreat. So that's certainly a question that we're very interested in answering.
Fabulous. Thanks very much. Thanks once again.
Any last questions?
Yeah, I had a question. I had my hand up in the.
Sorry, I probably can't see
right.
hands up. Sorry, Jonathan.
Okay, no worries, no worries. A great talk. I really enjoyed that, Alex. Thanks for that. At what point does basal roughness become topography? And I realise there's not a one answer to that, but I did notice that in your, your synthetic bump experiment or simulation, the basal roughness was 10 meters, which it wasn't unitless or normalized. It actually seemed to have a value. I would have expected that to be more like roughness, for like 1,000-meter thickness ice or something.
Mm-hmm. It sort of depends on what the broader state of the ice sheet and of the roughness is, right? So in the context of those idealized simulations, like the bed is perfectly flat everywhere. So a 10-meter sill will not be roughness, right? It'll be something that the grounding line cares about. Obviously, if there's roughness, of that order, amplitude everywhere, then that potentially starts to play into that. But I think the question of like what is roughness versus like what is topography really I think has to do more with the horizontal scales, because those horizontal scales affect sort of how ice sheet flow, which is primarily in the horizontal, which is why we make sort of the various approximations, sort of thin ice approximations that we do. The horizontal scales will end up determining sort of how the ice sheet sees that. And I can't offer, a much better theory than sort of the typical, I think, it's not even a rule of thumb, but the typical idea is that below one ice sheet thickness, the surface elevation or surface dynamics no longer sort of see that, or it is no longer translated, roughness is no longer translated to the surface below horizontal scales of one ice sheet thickness. And above that, it starts to become important to the larger scale dynamics of flow. So that is sort of usually how I think about it, is sort of horizontal scales of one ice sheet thickness. That's like the kind of crossover point. But I agree with you in the sense that what some of this work suggests is that topography really is important over lots of vertical scales, over a wide range of vertical scales. And so this presents a bit of a challenge for sort of thinking about like how accurate does our subglacial topography have to be, and how important is that for our projections of individual glacier change.
Yeah, no, thanks for that.
Thanks.
Okay, thanks very much. I'm just hopefully going to share the slide for next week's seminar. Hopefully that's just come up. So thank you very much indeed, Alex. That was an absolutely fabulous talk. I really, really enjoy modelling talks where you can understand all of it. It's fabulous. And then next week, we have talks by early career scientists. So please come along next week, and see you all then.
Tavy, I think you're showing your word, not your slide.
Oh, that's very unhelpful.
Well, thanks, everybody. I appreciate it.
Is that the right thing, or is it still my attempt to?
That's it. Yeah, that's it.
Brilliant. Fabulous. Right. Well, thank you for letting me know, Alex, and thank you all for coming, and thank you for a fabulous talk. So see you next week.